Hey everyone, today we're going to crack open the Problem Solver's Toolkit. We're going to explore two really fundamental ideas, regression and gradient descent. And these aren't just for finding patterns or predicting the future, they're actually the hidden engine behind some of the most powerful AI in the world. So here's how we're going to break it down. We'll start with the big picture. How do we turn a bunch of data into actual decisions? Then we'll get into the art of finding the best fit for a messy problem, sometimes with just a simple line. After that, we'll pop the hood and look at gradient descent, the engine that makes it all work. And we'll finish up by adding a few more advanced tools to our kit for building even smarter, more reliable models. All right, first up, from data to decisions. You know, when you get right down to it, a ton of machine learning boils down to one simple goal: using what we know right now to make a really good, educated guess about what's going to happen next. And that leads to this central question. Whether you're trying to forecast sales, figure out what a house is worth, or assess financial risk, it all starts right here. And in supervised machine learning, it turns out there are two main paths to get an answer. Those two paths are called regression and classification. Regression is what you use when you want to predict a specific number on a continuous scale. Think price, temperature, or height. Classification, on the other hand, is all about putting things into buckets. Is this email spam or not spam? Is this tumor benign or malignant? For the rest of our time today, we're going to park classification to the side and focus completely on regression. So that brings us to Section 2, the art of best fit. Let's start with the most fundamental, the most important tool in our entire regression toolkit: linear regression. So what is regression analysis, really? Well, put simply, it's all about finding the relationship between the thing you want to predict, we call that the target, and all the other data you have that might influence it. Those are your features. The whole point is to build a model that describes exactly how those things are connected. And the simplest version of this by far is linear regression. Just picture it. You plot all of your data points on a graph. The job of linear regression is to find the one single straight line that best cuts through all that data, capturing the main trend. That best fit line is your model. From now on, for any new piece of data, its prediction is just where it lands on that line. All right, Section 3, finding the bottom. Now, we've been talking about this magical best fit line, but how does a computer actually find it? There are literally infinite possibilities. This is where we meet the incredible engine that drives so much of machine learning: gradient descent. This is the million-dollar question, right? You could draw an infinite number of lines through a bunch of data points. So how on earth does an algorithm know it has found the one that's the least wrong, the one that really is the best possible fit? The answer is a brilliant optimization algorithm called gradient descent. And the analogy for it is just perfect. Imagine you're standing on a foggy mountainside, and your goal is to get to the very lowest point in the valley. You can't see the bottom, but you can feel the ground right under your feet. So what do? You take a small step in the steepest downhill direction you can find. Then you stop, feel the ground again, and take another step. If you keep doing that over and over, you'll eventually find yourself at the bottom. That is exactly what gradient descent does with the error of our model. So here's the play-by-play. The algorithm starts with a totally random guess, a random line on the graph. Then it measures how wrong it is. We call this the loss or the error. Next, using a little bit of calculus, it finds the gradient, which is just a fancy word for the steepest downhill direction to reduce that error. It nudges the line just a tiny bit in that direction, and then it does the whole thing over again. Step by step by step, it walks the line down this hill of error until it can't go any lower. It has found the bottom of the valley. Now, this engine has a few different gears. You've got batch gradient descent, which uses all your data for every single step. It's super slow, but very steady. Then there's stochastic gradient descent, which only uses one data point at a time. It's way faster, but it kind of zigzags all over the place. For most modern applications, the winner is mini batch gradient descent. It uses a small, manageable chunk of data, giving you the best of both worlds, a great balance of speed and stability. Okay, on to Section 4, the right tool for the job. A simple, straight line is a fantastic starting point, but let's be honest, real-world problems are rarely that simple. It's time to expand our toolkit a little bit. Yeah, sometimes the relationships in your data are curved, or maybe the thing you're trying to predict isn't a continuous number at all. A good problem solver knows you can't fix everything with just a hammer, so let's look at a few other types of regression models. Okay, so we've already covered linear regression for predicting numbers. Now, logistic regression is an interesting one. Even though it has regression in the name, it's actually for classification problems. It works by outputting a probability, a number between 0 and 1. You can then just set a threshold like 0.5 to make a yes or no decision. And finally, there's polynomial regression. This one lets us move beyond straight lines and actually model more complex curved relationships in our data. And for our final section, we're going to learn a real pro move, a technique to make our models way more robust and reliable. Let's get into Section 5, building smarter models with regularization. So here's a problem to think about. What happens when our model gets a little too good at fitting our training data? What if it starts to memorize all the random noise and tiny quirks instead of the actual underlying pattern? This is a huge problem in machine learning, and it's called overfitting. An overfit model looks amazing on the data it trained on, but it completely falls apart when it sees new data for the first time. The solution is a really clever technique called regularization. It basically changes the rules of the game for the model. It adds a penalty for complexity into the learning process. It essentially tells the model, hey, I want you to find a good fit, but I'm going to penalize you if you make it overly complicated. This forces the model to stay simpler and focus on the real signal, which makes it perform much better on new data it's never seen before. Now, the two most common types of this are called ridge and lasso. They both work by penalizing the model's coefficients, which are just the numbers that determine the shape of our line. Ridge does this by penalizing the squared value of those numbers, which shrinks them all down. Lasso, on the other hand, penalizes the absolute value. And this tiny mathematical difference leads to a dramatically different outcome. And you can really see that core difference right here. Ridge's smooth penalty shrinks the importance of every feature, but it keeps all of them in the game. Lasso's penalty is more sharp-cornered. It's much more aggressive. It can actually force the coefficients of the least important features all the way to 0, which effectively kicks them out of the model entirely. So Lasso doesn't just prevent overfitting, it also performs feature selection, telling you which variables actually matter. So the choice between them is strategic. You want to use ridge when you have a strong belief that most of your features are probably relevant. But you'd use Lasso when you have a whole bunch of features and you suspect many of them are just useless noise. Lasso will act like a filter, helping you build a simpler model based only on the signals that truly count. And if you're thinking, okay, this is interesting, but isn't this all a bit old school? Think again. These ideas are anything but outdated. As this quote from IBM points out, that core engine of gradient descent is still the backbone of how massive neural networks and transformer models, the very engines of modern AI, learn how to do what they do. So think about the journey we just took. We went from drawing a simple line to understanding the powerful engine of gradient descent and even added advanced tools like regularization to our belt. This isn't just a lesson in statistics. This toolkit is the fundamental language that so much of modern AI uses to learn. So we have these tools that can turn raw, messy data into real insight and powerful predictions. The only question left is, what are we going to predict next? Thanks for watching.